Hello class and welcome to 7.6 Solving Systems with Gaussian Elimination. In this section we're going to discuss how to use a matrix and this method, this Gaussian elimination method, in order to solve systems of equations. Now let's first discuss what a matrix is. So now a matrix is used to display information and to use, like I mentioned, to solve systems of linear equations. This value here is referred to as an element in the matrix. So EMN is an element where the letter M and N determines again the position of the matrix. M represents the row that the element is in, and N represents the column that we can find the matrix in. So our rows go down, our columns go sideways. So we have the element E2, 3. That means that this element is in the second row. You can find that element in row 2 and column 3. Of course, these elements would be actual numerical values. All right, they're not just going to be some random elements. There'll be, again, integers that correlate again to the system of equations. So let's discuss how that what that means. Now, while there are various types of matrices, the matrix we're going to be working with is referred to as an augmented matrix. Meaning that there is two parts to this matrix where the vertical bar is going to separate the columns of the matrix into two groups. The coefficients of each variable to this system are going to be placed on the left side of the vertical line, and the constant, the solution that each equation equals, is going to be placed on the right side. So if variables are missing, its coefficient is the number 0. So like example here, in this example, the system of linear equations translated into a matrix will look like this. So this row right here correlates to the column values of the x variable, the y, the z, and again what the constant, what the solution to this thing is in this row here. So here, this row correlates to this row, and notice that the value of 0 is in the middle because there is no x term. So we have one x, a one z, so represented by the two ones, and it equals to the value of 19. And then we have the last row, which correlates again to this last row right here on this augmented matrix there. Now, not every augmented matrix has this vertical line there, depending again on the format and the software that you're using. Sometimes this augmented matrix will not display it there. But if in the instruction or the definition of the explanation of this matrix is referred to as augmented matrix, then we know that the last column here, these values here, are going to represent what the solution to the equation is. So just keep that in mind, just in case you don't see this line here on every matrix that we write, or if I accidentally don't write it or purposely don't write it, just know that this last column refers to those values there. So let's look at some examples of how to write a system into an augmented matrix. So our first task before we go into any type of elimination, we have to understand how to write these systems into augmented matrix. So in this situation here, our first row is missing an x term, so that means that there are 0 x values. So our first row of our augmented matrix will look like this. We have 0, 2, a -1, because of the -1 and the invisible 1 there, and that's going to equal to the value of 7. And then our second row, that row would look like this. We would have 1, 2, +1, -17. And our third row, that would be 2, -3, +2, and -1. So here is your augmented matrix. Let's now move on to the second example. So in this second example, again, just going from one row to another, or you could even do it by columns if you want to create your augmented matrix first and then just fill in the values. You could also do it like that and just fill it by column. So in the first column are going to be our x values, which we have 1, 2, and 0. In the second columns are going to be the coefficients of y, which in row 1 are -2, row 2 is +3, and row 3 is +1. And then in the third column, we'll have the coefficients for our variable z, which in the first row is 0z, 1z in the second row, and -4z in the third row. And then on the third column, it'll be 2, 11, and -7. So here, just a different perspective of creating again our matrix in terms of columns instead of focusing on the rows. But you can clearly see that it's the exact same value had I done it from left to right instead of up and down. So let's now flip it and reverse it. So now we're given an augmented matrix. Let's write our system of equations. So this one I do want to definitely do in rows and not try to do this in columns. So for the first row, assuming that the variables are going to be the letters x, y, and z, because they could honestly be anything, but we'll keep it safe and simple and assume that the variables are going to be x, y, and z. For the first row, we are going to have -6x minus 8y plus 1z equals to a total of 20. For the second row, we have 0 x's, -8y's plus 6z's, and that has to equal to a total of 92. And for the last row, we have -3x minus 4y plus another 6z, but that one equals to a total of 43. So here is your system from your matrix. Moving on to the next example, the system for this matrix would be 7x plus 0 y's. We have 4 z's, and that equals to -13. In the second row, we have 0 x's, 1 y, or just y, minus 5z equals 11. And then on the third row, we have 2x plus 7y and 0 z's, and that equals 6. So here is the system to this augmented matrix. So now that we got the foundation down again of what a matrix is and how to write a system into this matrix, how do we use these? So the way to use this is that we want to perform operations to this matrix and to the rows of these matrix by using one of the three following operations. So the following row operations produce matrices that represent systems with the same solution set. And one of the things we're allowed to do with matrix is simply do a switcheroo, interchange the elements of the ith and jth row using this notation here. So this notation simply means to switch row I with row j. So take, for example, 3a. Here we have our augmented matrix, and we want to perform this operation right here. R1 interchange with R2. So that means that we want to get row 1, which is this row right here, and interchange it with row 2, which is that one right there. So our augmented matrix is going to be transformed to the following, to 1, 2, -3, and 5, and our row 2 would be 3, 18, -12, and 21. And row 3 would not change at all. So this is a operation that we are allowed to do with matrices, simple interchanging of two rows. The second operation allowed to do with matrices is that the elements in any row may be multiplied by a non-zero number. So, and what happens there is that you multiply each element in the row by some value of k. So the notation for that looks like this: k times I representing again the row that we're going to multiply. Take for example, example 3b. So here we want to perform the following row operation. Operation 1/3 of R1, which means we're going to simply multiply 1/3. We're going to multiply the number 1/3 with all the elements in R1. And R1 has the numbers 3, 18, -12, and of course the 21. And we want all of these numbers to be multiplied with that value of R1. So doing that, we're going to get the following. We're going to get the number 1, 6, -4, and 7. And this is going to be the new R1 in our matrix. So performing this operation is going to create the following matrix. And lastly, the last operation we're allowed to do with matrices is that each element in a row is multiplied by a non-zero number, just like we did in example 2, but then we add that product to a corresponding element in another row. So adding k times the element in row I to the corresponding element in a row j, which the notation will look like this. Now what's important about this right here is what new row that gets created here is this new row j. So we end up creating a new row j here, even though we're performing technically two operations. We're multiplying our row I, with some constant, non-zero constant, and then adding that to this row j. But as a result, this is going to create a new row j. So let's look at this example that we have here in 3C. So we here again our matrix, and we want to perform this operation here. So we have this scalar 2 that wants to be multiplied with row 2, which is this row right here. And we want to add that answer to row 3, which is this row right there. So what this operation is going to do, this is going to end up creating a new row 3. So row 1 and 2 are going to stay the same. So let me draw my augmented matrix down here. And then knowing that 3, 18, -12, and 21 are not going to change. The same thing with 1, 2, -3, and 5 are not going to change. And the only thing that's going to change is this new row right there. So this operation right here is a little bit more complex, because even though we're technically multiplying row 2 with 2, row 2 with 2, we're not going to change it here when we create this new matrix. We're only going to change this row there. So this is what we're doing, okay? So again, we have 2, and we want to multiply row 2 with that 2. So the elements in row 2 are 1, 2, -3, and 5. And we are going to add that answer with the elements in row 3, which are -2, -3, 4, and -6. You know what? I'm going to put this underneath here so you could see how this works, okay? And let me put that plus sign right there. So let me draw an arrow going that direction. So multiplying again, row 2 with 2, we're going to get this new number for row 2. We're going to get 2, 4, -6, and 10. And we're going to add those numbers with, again, like I said, with row 2. -2, -3, 4, and -6. Which are going to be 0, 1, -2, and 10 plus -6 is 4. So these are going to be the new elements for row 3. So -2, -3, 4, and -6. Let me show you a nice little shortcut that we can use Desmos for to do this operation. So again, as promised, let me show you how to use Desmos to do this operation. You're going to find it more efficient, hopefully. I prefer just doing it by hand, isn't that it's just multiplying and adding, but I know how we can easily mix the numbers up and keep things organized. So for anyone that wishes to do this, you can. So I first of all, notice again, I start by clicking on this plus sign there and inserting a table. This is not the only way of doing it, but to me, this is the most easiest and most organized way to do this. And I start by changing some things, okay? So I'm using row 2 and row 3, so I'm just gonna use those names, R, and then type in the 2, and then underneath here, type in the elements of row 2. So we have 1, 2, -3, and +5. And here I'm gonna change this to row 3 because I need those elements as well, which again are -2, -3, -3, oh gosh, +4, and -6. Ignore again what's going on in the graph. We only care about these values there, okay? And then here we're gonna add, again, notice that we have another column here. In this column here, I'm gonna write the operation I wanna perform. So I'm gonna do 2 of row 2 and add that with row 3. And because they're already labeled here, it adds them for me. And look, their numbers will match up. We end with numbers with number 0, 1, -2, and 4. So now let's look at this example here. So in this example, this operation is going to create a new row 3 again, because that's the one that we're adding it to. So we're multiplying our row 1 by this -2/3. And we're going to add that answer to this row 3. So multiply those by that and add it with that. Okay. And again, what's going to change here is not going to be row 1 and or row 2, but only row 3. So in this new matrix that we're going to create, our first 2 rows are going to stay the same. So let's see, let me write this stuff down. We have -2/3 times row 1, which has elements 3, 18, -12, and 21. We're going to add that to the elements in row 3, which those elements are -2, -3, 4, and -6. Now I'm just going to do this on the calculator. So just like the last example, I have my table here. And again, I'm calling it row 1, row 3. Those are the things that I'm using. So I can type in the expression exactly. So -2/3 times row 1. Okay, that's going to give me those values there. And then I'm going to add that to the element in row 3, which gives me those values. So my answer is this new row will have those numbers there: -4, -15, 12, and -20. And if I do it step by step, multiplying these numbers here by -2/3 will give us that. And then adding these values again in this order. So each element is going to correspond to the element in the given space, in the given row. In the, the given column. So this element here in the first column will only add up to this element here in that column, which is how we end up with the value of 0. I'm sorry, negative 4, because they're adding, not subtracting. Negative 2 plus negative 2, we end up with negative 15, like I mentioned. Positive 12, because 4 plus, hold on, that's not right. I messed up somewhere. Oh, that's an 8. That should be an 8. I messed up on my math here. That should be an 8. Oh. Which is going to be 12. 8 plus 4. And then negative 16 plus negative 6. Negative 14 plus negative 6. Sorry about that. That equals negative 20. So that's how you would do it again without plugging it all into the table and using decimals to add these values up. All right, now that we've gone over the operators for matrices, matrix operations, the idea, what is it used for? Well, the idea is that we use these operations in order to perform what's called the Gaussian elimination, named after a French mathematician, Frederick Gauss, in order to create a specific form of a matrix that, by performing these operations, is going to create two matrices that are called row equivalents. Meaning that this matrix here is equal to this matrix there. And the same thing with all these other operations, that this matrix right here is the exact same thing as this matrix, or equivalent to this matrix. Obviously not the same because it doesn't look the same, but equivalent to this matrix because we performed one of these three operations. And if we perform these operations in a specific order, we can create a matrix that can help us again solve a system of equations. So let's look at an example of that. So like I mentioned earlier, the process used to solve systems of linear equations using matrix row operations is called the Gaussian elimination after, German mathematician Carl Friedrich Gauss. Now, you begin by first writing your augmented matrix for the system, and then using row operations to simplify the matrix to row equivalent matrix form, which is called the row echelon form, where the values here of your main diagonal are going to be elements of 1. So if I can make these elements, again, the coefficients of this main diagonal 1, I can then use backward substitution from this step here and figure out the solution to this system. Now, there's not a specific order that you need to perform these three steps. It's not like you do the first operation, then the second, and the third. You have to, again, be able to manipulate this and determine, again, what you need to do in order to get these values. Now, the numbers underneath these, the main diagonals being 1, need to be the value of 0. And we'll see again and explain why in a second. So let's look at a very simple ones, again, with a matrix, with only 2 variables, 2 rows, 3 columns, and how we use, again, these matrix operations to solve. So here we have our matrix, our system, and we want to create it into a matrix. So the equivalent form of this matrix, I'm going to put it down here. In the first row will be the elements of 1, 4, and negative 8. And the second row is 8, 12, and 16. So we're going to just do this on a 2 by 3 matrix. 2 rows, 3 columns. Okay? So in this row is the first equation, and in the second row is the second equation. Our objective here is to get this main diagonal here to be just the number 1 and the numbers underneath to be the number 0. So here I'm already started in a good place because this value is already 1. I just need this number down here to be the number 0. And in order to get a number to become 0, we're going to use the third operator. That's the only way to get these things to be 0 down here, is by multiplying this number up here, these elements in this row, by some value. So when I add it to this one, this element right there is going to be 0. So it does give you an idea of what operation you need to do depending on what you want to do. So if I want an element underneath the main diagonal to be 0, that means I want to use the row above it, which is row 1, multiply that with some specific number. So when I add it to row, in this case row 2, it's going to create a new row 2 where the first element is going to be 0 and some number there and then some number right there, okay? So the key value here is, okay, what number can I multiply 1? So when I add it with a positive 8, it ends up equaling 0. Well, the only way to get any two numbers to equal to 0 is if I'm adding, in terms of addition, is if I'm adding opposite values. A positive x plus a negative x equals 0. So I need this to be a negative 8. So if I multiply the top row with a negative 8 and add it with row number 2, that will give me my new row that will be in this format there. And to help me again keep all of this stuff in order, I'm going to use my table. So here I have the elements in row 1 underneath and the elements in row 2 underneath. And I want to perform this operation of negative 8 times row 1 plus row 2. And again, how do I know this number was going to be negative 8? Because again, if you look at it like this, again, I want these two numbers to equal to this value of 0. So the only way I can add something to an 8 to get 0 is if that value is the opposite, negative 8. And that's why it's important again to have this value equal to 1. Because all you have to do is just simply multiply by the opposite of this number there, and that guarantees you to get a 0 in that place value. So this is going to be the new element of row number 2. So again, with the elements in row 1 being the same, 1, 4, and negative 8, the elements in row 2 are going to be now 0, negative 20, and 16. Okay? So again, recap, I have this value 1, but I also need this number right here because that diagonal right there, I need every element in these diagonal from this point here across to be the value of 1. So right here, I just need to change this to a 1. We'll recall, one of the operations again is the scalar multiplication. I can multiply by any value that I want. And to multiply a number so it becomes 1, you multiply by the reciprocal of that number. Basically divide by this quantity. So if I get negative 20 and I divide it by negative 20, that equals to 1. And to divide, that's the equivalency of multiplying by the reciprocal. So the operation I'm going to do to row 2 is to multiply that value by negative 1 over 20 by its reciprocal. And that's going to create a new row 2. Now, since I have the elements of row 1 and row 2 here, I just need to update this. The new elements in row 2 are 0, negative 20, and 80. And I want to, like I mentioned, do the reciprocal of 20, so 1 over 20 with that second row. So these are going to be the elements of the new elements of row 2 after performing this matrix, this row operation. So by performing these two row operations, we create again an equivalence matrix. So this matrix up here is equal to this matrix by doing this operation there, and by performing this operation, this matrix right there is equal to that one, which means this one is also equal to that one. Well, how is this matrix going to be helpful? Well, if we read, again, this matrix right here, specifically the last row here, read this right there, this is telling us something. This is telling us that 0x's, let me do it in red, 0x's plus 1y equals negative 4. 0x's is obsolete. We don't have to worry about that. And 1y, well, that's just y. So this has just given us what the value of y equals. Y equals to negative 4. And because we know what the value of y is, and we only have two variables to solve for, we can now use this equation up here, which is 1x plus 4y equals negative 8, and solve that equation because now we know what the value of y is. So we can replace the y value here with the number negative 4, which simply requires us to multiply these two, which is negative 16. We're going to move the 16 to the other side, making it positive. So the value of x is negative 2. So by performing these row operations and making sure again that this main diagonal again are ones, ultimately we're going to have one row that's going to just to be the 1, and all the other elements in that row before it are going to be 0. So we'll have 0 x's, 0 y's again, if we had 3 of them, and we can figure out what the value is. So here, we now know the solution to this system of equation. This system of equation is going to have an x value of 2, of x equals negative 2, and a y value of negative 4, which we call, because it's a system of equation, is basically just a point. It's a point of intersection. So these two things are going to intersect at this value there. Now the reason I did this example is just so you could see what the steps are, but of course this again is more useful and a little longer, of course, when we do it with multiple variables, when we have 3 variables and 3 equations. So we create a 3 by 4 matrix instead of this 2 by 3 matrix. So let's look at another example. So here, let's start by converting the system into a matrix. So in the first row, we'll have 2, negative 1, and 8. And in the second row, we'll have 1, negative 3, and, positive 3, and then negative 3. So again, we need the main diagonal to be ones. But if you look at the second row, the first element in that second row is already a 1. And one of the operations that I'm allowed to do is just simply switch 2 rows. So what I'm going to do here is simply switch row 1 with row 2, and now guarantee that one of the elements in the main diagonal, this one right here specifically, is now going to be the number 1. So there, my main diagonal here is already a 1. Now I need, before I can make this main diagonal be a 1, I need the element underneath this one here to be the number 0. And in order to do that, that's going to require again the third operation. Multiplying this row by a scalar and then adding it to this one to make this into a 0. So I want to multiply row 1 with some value, add it with row 2 to create a new row 2 that is in this format. 0, then some number, and of course my other number equal to some value. So what number can I multiply by? Row 1, so when I add it with row 2, it guarantees me that this number right here is going to be 0. Well, simply the opposite. So this number is 1, simply multiply 1 with the opposite of this number. So I'm going to multiply by negative 2. Alright, so here I'm going to create this new row 2 by, like I mentioned, multiplying row 1 with negative 2. So negative 2 times row 1, and then adding that with row 2. So this right here is going to be my new elements in row 2. 0, negative 7, and 14. So now with the new elements in row 2 being 0, negative 7, and 14, again, let me highlight my main diagonal, and this number being 0, I can now focus on this element of the main diagonal and try to make it 1. Well, to make an element 1 simply means to divide by that number, which is the equivalency of multiplying by the reciprocal. So on row 2, I'm going to multiply everything by negative 1 over 7, which, like I mentioned, is essentially the same thing as dividing by 2, dividing by negative 7. So even though I write it as a multiplication, mathematically, I'm just dividing by 7. So row 1 is going to stay the same. And dividing by 7, well, 0 divided by 7 is 0. Negative 7 divided by negative 7 is 1. And 14 divided by negative 7 is 2. And now that I have this, I can now use this last row here, just like last time. And I have 0x, 1y, and I know that the value of 1y is now negative 2. And using backward substitution, I can now focus with this row up there, which states that this is 1x plus 3y's equals negative 3. And since we know that the value of y is now negative 2, I can make that substitution. So all I'm doing is replacing that into there. Simplifying by multiplying these two, that's going to give us negative 6. Moving the 6 to the other side, so making it positive 6, gives us that the value of x is positive 3. So x equals 3, y equals negative 2, which as an ordered pair means 3, negative 2. And there's your solution. Now the goal is to be able to do this type of situation and these type of procedures to matrices with 3 variables in order to produce ones down the main diagonal, in order to get exactly that, the exact same format, okay? By getting these main diagonals equal to 1, we refer to this format or this form as row echelon. So we want to create a row echelon form of this matrix, and where A through F are going to be any real number. So these values here, A through F, okay, are going to be any real numbers. The third row of this matrix is used as the value of one of the variables. We can then use that one variable and go backwards using backward substitution to figure out the other 2 variables that are missing. So if your matrix is already in row echelon form, then we can just simply identify what the values of my variables are by using back substitution, as you'll see in this example. So take into account example 4a. So here I have a matrix, a system of equations, and the row operations have already been performed for you. All that's left to do is to use, again, the echelon form of this matrix to the row echelon form of this matrix in order to solve the system and figure out what the variables are. Let's assume, first of all, that the variables are in columns of x, y, and z, okay? So starting off with the last row, we know that x equals, I'm sorry, not x, z, 1z, equals to positive 2. And I kind of got ahead of myself. I forgot to mention this. How do I know that, first of all, that this is even in row echelon form? Because if I look at the main diagonals, all of those elements are 1, and the elements below those are 0. So underneath that 1, the elements below that in that row are 0, and below this one right here, the elements below that one is 0. And of course, in the last row, we only have the value of 1 right there. All the elements in front are 0, and all the elements in front of that right there are 0. So you can think about it like that. So as long as the main diagonals are 1s and the elements below or to the left of the main diagonals are 0s, then this is in row echelon form. So with the last row telling us that the value of z equals 1, we can now use backward substitution. We can now look at the row above it, which states that 0x plus, again 0, so 0x plus 1y, which is just y by itself, minus 1z, which is just negative z, equals negative 3. I'll put the negative 1z because I'm going to do a substitution. And knowing from the last row that z equals to 2, we can do backward substitution. So y minus 1 times this value of z, which is 2, equals negative 3. Multiplying these two numbers here, that's going to be negative 2 equals negative 3. Moving the 2 to the other side, y equals negative 3 plus 2, and we get that the value of y is negative 1. And then moving upwards, sorry, I meant to get them highlighted. Moving upwards, this row right there tells us that 1x minus 1/2 y plus 1/2 z, that's going to equal to 5 over 2. But we know what the value of y and z are. We know that the value of y is negative 1. We know that the value of z is positive 2. So making those substitution, we can now solve this equation for x. So x minus negative 1/2 times 1, that's positive 1/2. 1/2 times 2, that's positive 1. We're going to move those elements to the other side. So they're going to become the opposite. And this is going to end up equaling to a total of 1. 5 over 2, which is 2.5, minus 0.5 is 2, and then 2 minus 1. These two equal to 2, and then 2 minus 1 equals 1. So there is our solution. Z is equal to 2, y equals negative 1, and x equals to 1, which as an ordered pair is 1, negative 1, and 2. X, y, and z. So let's look at the next example. So first of all, notice that in this next matrix, the row operations have been done. So we now have a matrix that is in row echelon form. All the main diagonal elements are 1, and all the numbers underneath those main diagonals are 0. So that means that if we focus on the last row here, we know that the value of z, assuming that the variables are still going to be x, y, and z, we know that this is going to be 1z, let me do it in red, 1z equals to a value of 1. So now we can use, using backward substitution, I can now use the second row where 0x, 1y, minus 2/3 z's equals negative 5 over 3. Substituting in the value of z from the third row, 1. We can multiply that 1 with negative 2/3, which is negative 2/3. And moving the 2/3 to the other side is going to give us that y equals to negative 2/3 plus a positive 2/3. And even though they're fractions, the numerators are the same, so you're just simply focusing on the denominators, are the same, so you're simply focusing on adding these numerators on top. So negative 5 plus a positive 2, that equals to negative 3. So negative 3 over 3, that equals negative 1. So there is your value of y equals negative 1. We can then go to the first row of this matrix. Oh, come on, highlighter. And using that first row of this matrix, we can now use backward substitutions and plug in both the x and the y value. So first of all, we need to be able to read this. Again, those skills that we built at the beginning of this section. So x plus 2y minus 1z equals negative 1. Replacing the x value, I'm sorry, the y value, because we don't know x, replacing the y value with 1 minus 1 times z, and replacing the z value with negative 1. We can now solve the equation for z. I'm sorry, for x. Sorry, all these variables, I'm saying the wrong things. I can now solve this equation for x. So x, this is 2. This is going to be 1. I can add these if I want to before I move into the other side. Doesn't matter the order. Let's do it that way this time. This is going to be a total of 3. And then I can move the 3 to the other side, making it negative 3. We end up with negative 4. So here are the solutions to each variable. Z is equal to 1, y is equal to negative 1, and x equals negative 4. Which can also be written like this in order: x, y, and z. All right, that concludes the first part to this lesson. I hope these examples were helpful. And even though, again, we're not going to be using or actually we won't be doing these operations. You'll do examples like this. I hope you got a good understanding of how to use row operations to create, again, this row echelon form of a matrix. Now, if you have any questions on the homework or anything else on this notes, please send me a message. And like always, I appreciate you watching, and I hope you have a good day.